All right, welcome to the Galvanic cell session. Remember the last time you remember these notes. These notes are not new to you. We had electrochemical reactions, and we said all these electrochemical reactions take place in a cell that we call electrochemical cell. And it is a device. Electrochemical cell is defined as a device where electrochemical, which we said a redox reaction, takes place. We said there are two types of these cells. We have galvanic and electrolytic. We mentioned the word electrode. We're going to use that just now, again, in our definition. Oh, by the way, just a reminder, so Krazifizix, we on with the class. All right, just Krazifizix. And now we're going to focus quickly on galvanic cells. Galvanic cells. Galvanic cell. Now the first thing is to define what a galvanic cell is. A galvanic cell is, of course, we know now it is an electrochemical cell. I'm sure we know that already because we talked about that. Electrochemical cell where chemical energy is converted. Remember we talked about energy conversion into electrical energy. And to put a picture in our mind quickly is just an example of this is your battery. Every battery, you use, you actually produce electricity, electrical energy by using what? Chemicals. So a galvanic cell is an electrochemical cell that converts electrical energy into converts chemical energy, into electrical energy. So galvanic cell converts chemical to electrical. That we need to know. We're going to come up with a code as we go on later. I want us to understand what a galvanic cell is made up of, and then we will do a few further explanations. A galvanic cell is made up of what you call half cells. Half cell is a cell where this redox reaction takes place, but in each of the cells, what makes up a cell? In each of the cell, number one reaction takes place there. It is either oxidation or reduction. So when we say half, remember we're talking about two reactions. So when we say half, it means one. So in half cell, it's either you have oxidation or you have what? Reduction. So a galvanic cell is made up of two half cells. Separate half cells. They must be separate. We'll see the diagram. What is an half cell? What is in one half cell? An half cell is made up of electrode. All right, we talked about electrode a while ago, and then you have an electrolyte. Okay, let me put that here. We have an electrolyte. An electrolyte is an ionic compound. It's an ionic compound in a liquid or in a okay, let me say an ionic compound, an ionic solution. Let's use the word solution, this might be just better. An ionic solution. It could be aqueous as well, that allows the movement of ions. All right, an electrolyte is an ionic. It must be ionic because we're talking about a transfer. So there must be free electrons to move. An ionic solution, or could be an aqueous solution as well, that allows the movement of ions, which means it gives free movement to electrons. So we're saying our half cell will consist of an electrode consist of an electrolyte. These ionic solutions, basically, they are salts. All right? And most of the time, we normally use the salt of the electrode. They must be of the same kind. For example, if I'm using zinc electrode, then I should use a zinc salt. Salt could be a chloride, it could be a nitrate, it could be a sulfate. So you could have your zinc chloride, your zinc nitrate, your zinc sulfate, any of the salts, because it must be an ionic salt. All right. So what again did we say? We said our half cell is a cell where either oxidation or reduction will take place. Our half cell consists of an electrode. We defined electrode, all right, earlier on. Uh, Electrolyte as well. So already, look, we're going to have something like, remember, we are trying to convert chemical energy to electrical. So we would have a simple diagram like this. This will represent our half cell, all right? And you have your electrolyte again. Let's call this the zinc half cell, and let's call this the copper half cell. So we have our zinc electrode, and then we have our copper electrode. This is copper, this has to be solid, and this is zinc as well. So in this case, we could have, let's have a zinc chloride salt here, and here we have a copper chloride. Could be sulfate, could be nitrate, but it has to just be a salt. Okay, but if you look at these two, they are not connected in any way. But we're trying to produce electricity. So let's have a wire here, and let's have a light bulb here. A very small resistance light bulb, very small resistance. Okay, but this cell is still incomplete. It's incomplete. There is a main part of this cell that we need to introduce, and this is called the salt bridge. The salt bridge is just serves as a connection between the two half cells. We will talk about the salt bridge just now. But now you can see that we have a complete circuit here. All right. What is a salt bridge? Let's quickly talk about a salt bridge, then we'll come back to the diagram. The salt bridge, this is a device used to connect, the two half cells of a galvanic cell. The two half cells of a galvanic cell. And what are the functions? Number one function, it completes the circuit. That's the first function. You saw in that diagram, the circuit was very open without the salt bridge. And number two, this is the other main function now. It maintains electrical neutrality. Within the circuit, within the internal circuit. Let's use the word internal. Within the internal circuit. And why is this so? This is so because it helps to prevent. It helps to prevent. It helps to prevent a rapid running of the reaction into equilibrium. Again, we're going to talk about Le Chatelier's principle here. All right. So this is the function of the salt bridge, a device used to connect the two half cells of a galvanic cell. It completes the circuit. It maintains electrical neutrality. All right. Um, so that this system does not reach equilibrium quickly. Because when it reaches equilibrium, we'll talk about that. It means the reaction just stops. The rate of the forward and the rate of the reverse reaction will now be equal. This will affect the state of our galvanic cell. Now, what are the things that make up a salt bridge? What are the things that make up a salt bridge? So let's look at the contents of a salt bridge. We've got to go to the next page. Contents of a salt bridge. All right. We're still looking at a salt bridge. The contents of a salt bridge, number one, it must be made of an inert electrolyte. Remember we talked about electrolyte a while ago? Inert. The word inert means something that is not reactive. Inert electrolyte. It mustn't react, with the contents of half cells. Inert electrode. Common examples are your potassium chloride, your sodium chloride. These are common examples. Your potassium nitrate, your sodium sulfate, sodium sulfate. These are our common examples that we would use regularly. So these are inert electrodes. When we say inert, we mean they should not react with the content. Otherwise, it will affect the chemical status of our half cells. We would understand how it works in just a while. Let's go back to, okay, we need to redraw this diagram because we moved to a different page now. We need to redraw this diagram. All right, let's have our zinc. We said we have light bulb, and then we have our copper. We have our copper salt. Basically, what we need in these electrolytes are the ions. So here, what we have basically would be zinc 2 plus ions. That's what we really need. So let's have zinc sulfate here. All right, and here we have copper sulfate. Remember, what we have here again is Cu2 plus copper ions and zinc ions, and then we have our salt bridge, and basically we can use our sodium here. Right? Good. We've got a cotton wool here, and we've got a cotton wool here. So we have a reaction here. Okay. Now I want to take time to explain to you what will happen in this reaction because it's our main focus in the session. We have zinc and copper. We said one of these cells will go through reduction and the other cell will go through oxidation. But I want to use this moment to explain to you which one would be reduced and which one will be oxidized. Which one will be reduced and which one will be oxidized. There is a table that we would need to use, a table that measures the reactivity of all these elements. I'm going to create a new page. Okay, I think I have a new page. I have a new page somewhere. Yes, good. And I'm going to use this. Because I'm going to need to expand this. Let's take a snapshot. I'm trying to avoid copying. Yes, I'm trying to avoid copying whether 4A or 4B. I'm interested in us understanding how the table really works. Right? Good. Here we are. Got our table here. Can you see it's called half reaction. This table is half reaction table. our half reaction table. Now, we're dealing with copper and zinc. But what I want us to first understand is we're dealing with copper 2 plus, and we have copper solid electrode, because on this table there are a few copper lines you would see, and we're dealing with zinc 2 plus and zinc. All right. I want us to check something on this table quickly. Let's check this arrow. What does this mean? Increasing oxidizing ability, and on the other side you would see increasing reducing ability. This arrow here is pointing up, and this one here is pointing down. What is the implication of this line pointing up and pointing down? Increasing oxidizing ability. It simply means that as you move up the table, the ability of these elements to oxidize increase. Okay, but saying the same thing written. Let's look for our copper and zinc, so I can use that to explain. I've seen copper, and we're trying to find where zinc is. I want to see if I can have them. All right, got it. I've got my zinc here. That's where I mark. And like I told you, I've got different copper. This is one copper. It's another copper. There should be one more. Okay, we've got on this particular page, we've got two different ones here. Now, here's a third one. Got it. Good. Now, if you notice here that this copper plus ion is losing one electron, when you have copper plus here, here we have copper 2 plus gaining 2 electrons, while this copper 2 plus is gaining 1 electron to still become a copper ion, but copper 1 ion. This one is moving from copper 1 to copper. But in this case, we are really moving from copper 2 plus to copper. So this is more ideal for us to use. So let's compare copper and zinc in this case. Copper and zinc. Now, it's space here because I don't want to move from here. Now we're saying that as you move up the table, remember this arrow. Is it okay therefore to say copper is a stronger oxidizing agent than zinc? Copper 2 plus. Cu2 plus is a stronger oxidizing agent than zinc 2 plus. Because that's what this table tells us. If I come to this side of the table, increasing reducing ability, it means zinc 2 plus is a stronger reducing agent, because as you move down the table, the ability to reduce increases. So zinc is a stronger reducing agent. It therefore makes it simple to say that since copper is a stronger oxidizing agent, copper 2 plus, it will be easily reduced. I'll say that again. Copper 2 plus is a stronger oxidizing agent. It will be easily reduced. Zinc 2 plus is a stronger reducing agent. It will be easily oxidized. I will explain this in different ways. So the first way is to look at the table and follow your arrow. So whether 4A or 4B, we just need to follow the arrow. This arrow says increasing oxidizing ability. As you go up, the one above are stronger oxidizing agents than the one below. So a stronger oxidizing agent will be easily reduced. We're saying it is easy for them to lose, it is easy for them to gain their electrons because they are stronger oxidizing agents. While the zinc is a stronger reducing agent, it will be easily oxidized. That's point number one. So point number one, the stronger oxidizing agents become easily reduced. So copper 2 plus is the stronger oxidizing agent than zinc. And the stronger reducing agent, zinc 2 plus is a stronger reducing agent, so it will be oxidized. All right, that's number one. Number two, I need us to look at these numbers here. There is a positive 0.34 and there is a negative 0.76. What is the implication of the positive and the negative in understanding this? Elements that are more positive are easily reduced. Elements with more positive, that's another way to look at it. Elements that are more reactive, this is more reactive. Okay, it's getting a whole lot messy here. Elements that are more reactive are easily reduced. So when you compare, the more positive ones are easily reduced. In case you're not given a table, you could be given values, are easily reduced. More positive are easily reduced. More negative are easily oxidized. Let's put this down in our notes. All right, let's put this down in our notes. I need us to have this in our notes. We say the first one, stronger oxidizing agents are easily reduced, and vice versa. We said more positive elements, when we talk about the potential, more positive elements are, or let me say, element with more positive values are easily what? Reduced. And also vice versa. If it's negative, it is oxidized. Negative is oxidized. I'll give you a couple of examples. All right, negative is oxidized. So in this case, we have ascertained. Let's go back to that table quickly just to check something. Now we have ascertained that copper 2 plus will be reduced. Where does reduction take place? Red cat. Reduction will always take place where? At the cathode. Okay, let's go back to our diagram. This is where we have copper, so this is going to be our cathode. And this is going to be, obviously becomes our what? Our anode. Is that clear? So we have anode, and then we have what? The cathode. Remember, what takes place at the anode is oxidation, and what takes place at the cathode is reduction. And what is oxidation? Oxidation is the loss of electron, while reduction is the gain of electron. This is what we basically mean. Electrons are lost from here. So electrons are migrating. Remember what we said? Transfer. If you remember the word transfer of electrons, electrons are migrating. So electrons move from the anode to the cathode. Electrons move from the anode to the cathode. Let's put down our notes again. Electrons move from anode. Why are they moving from anode? Because they are lost, to the cathode, because that's where we gain electrons from. We need to quickly identify the terminals. All right, we need to quickly identify the terminals. We said galvanic cell converts what? Chemical to electrical. Is that okay? Now, I needed to understand that in a galvanic cell, the cathode is the positive terminal. I'm going to tell you later how to remember this quickly, while the anode is the negative terminal. Cathode is the positive. This diagram is going to get messy, but you need to follow through. So here we have our positive terminal, and here we have our negative terminal. I want you to watch this. In grade 10, when we started dealing with circuits, we have a symbol of a cell like that. And we say this is positive and negative. Current will always move from positive through to negative. The same thing happens here. Current will move from the positive to the negative. So conventional current would move from the positive to the negative, while electrons would move from the negative to the positive. Very important point. Current would move from the positive down to the negative. That's how it moves. Remember the cell or this diagram. But electrons will move from where they are lost to where they are gained. These are good points where an examiner wants to ask you certain questions. An examiner wants to check if you understand the movement of electrons and the movement of current. All right, so we understand the movement of that. I'm going to net the space, so let me clean this. Net the space. Broke my salt bridge. All right, we have that back. So we understand that oxidation takes place right here and reduction takes place right here. Remember what we said? Oxidation is the loss of electron. So what is losing electron actually? That's a question I want us to deal with. What is it that is losing electrons? And what is it that is gaining electron? And what is the impact of that? You know, if we have this as our solid, remember we said it must be solid. Now, zinc. Zinc is what is actually losing. All right, let's do this. Okay. We have zinc, and then we have copper here on the side. Here we say we have oxidation. What has been oxidized? Now, zinc is actually being oxidized because zinc is a solid metal which needs to lose electrons. So zinc is being oxidized by losing electron and becoming what? Zinc 2 plus. But remember what we said in our first session. We don't write it like this. It has to be written this way. This is called our oxidation half-cell reaction. And what does this basically mean? It means that the zinc metal solid is dissolving. I'm going to play a video for you later on. It's dissolving into the solution. So which means there is a loss in mass. It is reducing in size. On the other hand, where you have the copper electrode, we said it is reduction. Invisible again, back to visible. What is being reduced? Copper 2 plus is gaining the 2 electrons. I'm going to go back to that diagram for an animation and becoming copper solid. So this again is called our half-cell reduction, half-cell reaction. What is happening here? We have copper 2 plus ions is being reduced to copper solid, which means there is an increase in mass. There is an increase in mass. Let's go back up quickly to get this very clearly. Look, electrons are moving from here, and these electrons come through this external circuit, and they get in here. Remember what we have in here, copper 2 plus. They gain these electrons, and they form copper solid. So at the end, you have copper solid here increasing in mass here, because it is being now changed from ions into what? Into solid. While this one, on the other hand, begins to decrease in size. This begins to decrease in size because it is dissolving into zinc 2 plus. As each electron moves, okay, we've got 2 electrons moving, all right, so that you have zinc 2 plus ions. Good. So we have electrons moving over here. So we have a deposit of electrons here. And therefore, this side becomes partially negative. It's more negative because there are electrons. And this guy becomes partially positive. Here, you have what you call a deficit of electrons because they are leaving. And here you have what? Excess, because it is being deposited electrons. So you have partially negative, and this becomes partially what? Positive. By the way, what is the function of this salt bridge? We've been talking about it all along, that it's there, but we've not mentioned it. Now, this salt bridge has an inert electrolyte. What will happen is the chemicals will break down into their ions. In this case, we have sulfate and we have sodium ions. Remember now that we said that this helps to maintain electrical neutrality. If the side is more negative, what will happen? The positive ions, which are called the cations, will move towards the side. And this side is more positive. The anions will migrate towards the anode so that it maintains electrical, what did we say? Electrical neutrality. And that's the way the salt bridge simply operates. Electrical neutrality. So let me add this to the notes again. The anions move towards the anode, and the cations move towards the what? The cathode. This is your salt bridge. That's how your salt bridge works. So we need to understand there's so many things going on at the same time. Oh, this diagram is becoming very, very lovely. If you didn't follow through from the beginning, you might just get confused on what this diagram is all about. But I'm sure we can, explain what's going on first. We said electrons are lost here. They move towards that side. Conventional current comes from this side and back to that side. This is the anode. The zinc loses mass. The copper gains mass because of reduction, and there's oxidation, partially positive, partially negative. The salt bridge cations and anions migrate to balance. And this is simply, now if you'd notice, this is your galvanic cell. If you'd notice, I need to talk about this bulb here. All we did was to connect these, and we expect that this light bulb would actually glow, which simply means that this reaction should be spontaneous. Using another word, this reaction should be spontaneous. Spontaneous means a reaction that takes place on its own. On its own. It's self-sustaining. And if a reaction is spontaneous, it is going to be exothermic. It's an exothermic reaction because it is spontaneous. We will later see how to do a calculation on to check on the spontaneity of a cell. But let's notice the reaction can take place on its own. Therefore, because the reaction is taking place on its own, it's going to be exothermic, which means it will be releasing heat. Have you ever felt your battery being hot? Probably this explains it. Releasing heat, exothermic reaction. All right. So much in one session, but we're not done. Now, we have our oxidation half cell. Oxidation half cell reaction. What did we say that is? Oxidation is where electrons have been lost. So we have zinc becoming zinc 2 plus 2e. While reduction is where we have 2 plus, copper 2 plus being reduced to copper. Now there is what you call the net ionic equation, which is also used for the word redox. Net ionic equation, that is what is happening. Remember we said these are two half cells. Now, what is happening in these two half cells combined together? This is very simple though. We'll look at a more complex example in the next session. All we need to do is to put what's on the left to the left. On the left here we've got zinc, so I'm going to have zinc solid. I have copper 2 plus. I have 2 electrons. Then on the right I have zinc 2 plus copper solid plus 2 electrons. Now if you notice the number of electrons here and the number of electrons here are the same, it simply cancels out. That's mathematics now. And then we are left with zinc solid. Do you remember this equation? That was the equation I used in explaining the reducing agent and oxidizing agent a while ago, plus copper solid. This is your net ionic equation. Net ionic equation. That's 3 marks if you're able to get it right in an exam. But remember, once you get your cathode and anode wrong, things might just be mercy. Therefore, that table needs to be well understood, where you identify which one is your cathode and which one is your anode. So you might need to rewind this presentation and keep checking on the anode and cathode to make sure you get it right. We'll still have some more examples to look at in the next session on looking at how to identify your anode and your cathode. Basically, we need to finish everything on this galvanic cell. All right, we're done with that. Now, we need to talk about what are the conditions. Let me just quickly talk about standard conditions. I need to mention this quickly. Standard conditions for a galvanic cell. Before I go into calculation for a galvanic cell, what are the standard conditions for a galvanic cell? First, we need to know we have standard concentration, and the standard concentration is simply 1 mole per dm cube. All right? Standard concentration, standard temperature, which is 25 degrees Celsius, but that's 298 Kelvin. I'm sure you know how to convert that. We add 273. And standard pressure, if we have to deal with gases, as we would see later on, would be 1 atmosphere, which is 101,3 kilo Pascal. All right, these are your standard conditions for a galvanic cell. It is important that we remember the standard conditions: 1 mole per dm cube concentration, and then you have your 298 Kelvin, and then your 1 atmosphere. The value of that is on your data sheet, which you would use, during exam. But we need to know. Remember, pressure only applicable when we have gases. Pressure is only applicable when we have the gases. Okay, so these are standard conditions that we need to know. Next, it's a whole lot of things on this galvanic cell, you know. There's what you call cell notation. How do we write our cell notation? The cell notation is it's very simple stuff. But still, we need to identify our anode and the cathode. Once we identify that, it becomes easy to write your cell notation. It's as simple as A, B, C. The cell notation is as simple as A, B, C. A meaning your anode, B represents your salt bridge, so we just use the word bridge, and then C is your cathode. So it's as simple as A, anode, bridge, and cathode. We need to start from the anode, then we go to the bridge, and then the cathode. What did we say is going on at the anode? We said it's oxidation. So this is how we start. We start with the anode. You start with the electrode. Zinc solid. We use a stroke there to represent a phase change. This represents a phase change. All right, so we have zinc changing into zinc 2 plus aqueous. Remember the standard, it's 1 mole per dm cube. That's our anode. Exactly what takes place at the anode, oxidation. And then we have a salt bridge represented with 2 arrows. And then we move to the cathode. If you scroll up, you'd see cathode is Cu2 plus again, 1 mole per dm what? 1 mole per dm cube, being converted, being reduced to copper solid. This is about 3 marks or 4 in your exam paper. This is your cell notation. So simple as A, B, C. A, anode, B, bridge, and C, we've got the cathode. All right, I think 2 more things that will be done on this session. How do we calculate the, oh, my E, very funny. The potential energy in the cell. On your formula page, it is written as E cathode minus E, oh my E, keep writing this funny E's, anode. Remember what's on the cathode? Our cathode is copper and anode is zinc. We need to go back to our table to check the values. Let's see if we can quickly pick that again. Good. Cathode, remember what we're using? 0,034, and our anode negative 0,76. So let's go back. 0,34 and negative 0,76. I hope this makes sense to you so far. 0,34, that's our cathode, minus this minus my negative 0,76. And this would give you 1,1 volts. Positive. Remember, this is a positive answer, which means it is spontaneous, and meaning it is an exothermic reaction. Exothermic reaction. Exothermic reaction. Probably need to play something for you, all right, while we're still on this, so that you'd get a better understanding of this. Let's see if I can get that for you. We said it's spontaneous.
A useful galvanic cell can be constructed by using zinc and copper. The anode is a zinc bar placed into a zinc sulfate solution. And the cathode is a copper bar placed into a copper 2 sulfate solution. The two solutions are connected by a porous sodium chloride salt bridge that prevents the two solutions from mixing but allows ions to migrate. Attaching a cell shows that electrons flow from zinc to copper. Because zinc is a more active metal than copper, it is more likely to lose electrons. For this reason, the zinc bar is oxidized, producing a zinc ion and 2 electrons per zinc atom. The copper ions in solution gain 2 electrons and are reduced to copper metal. As the reaction continues, excess positive zinc ions build up in the zinc solution. At the same time, the loss of copper ions from the copper sulfate solution creates an excess of negative sulfate ions. Positive sodium ions migrate into the copper sulfate solution from the salt bridge, while negative chloride ions migrate from the salt bridge to the zinc solution and maintain neutrality of the solutions. The reaction stops when the zinc bar or copper ions are depleted. The overall cell reaction can be written like this.
Now, I hope that video makes a bit of sense to you to help you understand some of the things that I've been trying to explain. I'm going to try to go back a bit, on this to make us see certain things here, right? Just to be able to highlight certain things here. Now, I need you to notice um, here we have the zinc, and the zinc we said will be oxidized, all right? That's a light bulb there. We've got a light bulb right there. And here is the other half cell, which has a copper, the copper half cell. Okay, we have got solutions there, which are both salts. Now, on this, okay, the salt bridge here is, sodium chloride has been used. Now, this is very important. Just setting up this makes the light bulb glow, which means it's a spontaneous reaction as it goes on. And on the zinc, you have zinc 2 plus. Every time zinc, do you see that the decrease in mass? Because it has been oxidized from zinc to zinc 2 plus. So the mass of this electrode actually decreases. While on the other hand, these electrons, help copper 2 plus to be reduced. As this zinc decreases, I need you to see the size here. The size here is increasing, okay? The size is increasing so that this one increases in mass because there's reduction from Cu2 plus to copper solid, from the invisible to the visible things that we can see. All right, so there's bound to be an increase in mass on that side. I hope this, helps us to understand, this animation helps us to understand what is really going on, and that's what I've been trying to explain the whole time. And you have your reaction, and remember we said it must be balanced, and then we have this balanced chemical reaction here. Okay, overall cell reaction. Remember, now we wrote we said it's spontaneous, 1,1 volts. We have, let me see if I can give you another shot on another video, right? Let's see quickly if we can get another one. think I do have another one.
A
Oh,
useful galvanic cell can
no, it's the same one here. Let me get you another one. All right, let's
be
delete this one.
constructed by using zinc and copper.
Let's delete this one and get the other one.
When a strip of zinc metal is immersed in an aqueous copper 2 sulfate solution, electrons are transferred from zinc to the copper 2 ions. Copper metal deposits on the zinc strip and collects at the bottom of the flask. Zinc atoms are oxidized to zinc 2 ions, which enter the solution. This spontaneous oxidation reduction reaction is summarized in the chemical equation shown. The spontaneous copper-zinc oxidation reduction reaction can be made to yield useful electrical work by incorporating it in a voltaic cell. The zinc electrode is immersed in a solution of zinc sulfate. The copper electrode is immersed in a solution of copper 2 sulfate. No current flows through the light bulb because the electrical circuit is not complete. To complete the electrical circuit, we add a tubular bridge filled with aqueous sodium sulfate solution with a porous plug on each end. We now have a complete circuit and current flows. When we replace the light bulb with a voltmeter, we find that the cell has a potential or voltage of 1.1 volts. The copper electrode is the positive electrode, and the zinc electrode is the negative electrode. As the cell reaction proceeds, zinc atoms of the zinc electrode lose electrons and move into the solution as zinc ions. At the same time, copper 2 ions acquire electrons at the copper electrode and form copper metal. The reaction in the left-hand compartment is oxidation of zinc. The electrode at which oxidation occurs is called the anode. The reaction in the right-hand compartment is reduction of copper. The electrode at which reduction occurs is called the cathode. Electrons flow from the anode to the cathode through the external circuit. To maintain electrical neutrality in the two cell compartments, ions must move through the salt bridge. In summary, remember that in a voltaic cell, the anode at which oxidation occurs is the negative electrode. The cathode at which reduction occurs is the positive electrode. Electrons flow through the external circuit from anode to cathode. When a strip of
All right, I think also that helps us to understand a few things. All right, conclusively in the session, please rewind over and over again. I quickly want to explain what we mean by a flat cell. I'm going to use Lechtelius principle to explain what we mean when we say the cell is flat. All right. Now, if you consider the reaction that we have a while ago, which has to do with the zinc and the copper, remember we said zinc is oxidized. So this is what we have. We have zinc plus Cu2 plus. This was our overall cell reaction, if you remember. Copper plus what? Zinc 2 plus. Okay. Now, I need you to notice that the Cu2 plus is being reduced to Cu, which simply means that this actually decreases in concentration. I'm sure you remember the symbol. Concentration of Cu2 plus does what? Decreases. And this creates an imbalance. Remember, Lechtelius principle talks about stress being created in an equilibrium, state of equilibrium. The equilibrium will shift in order to minimize the stress until a new equilibrium is attained. So let's see this. As Cu decreases due to the reduction, this one here, the zinc, remember zinc is being oxidized to zinc 2 plus. So there's going to be an increase in concentration of the zinc 2 plus ions. You saw in that video the electrode was dissolving into the solution. What will happen now? This changes in concentration creates a stress on the system. the equilibrium will shift to minimize the stress caused by the change in this concentration. And the question is, how will it shift? It will shift to favor, since this is where there's a decrease, here there's an increase. It will shift to favor the reverse reaction. When it favors the reverse reaction, it means it will shift so that more of Cu2 plus ions is also now what? Formed. More of Cu2 plus ions is not formed. This will continue until a new equilibrium. Now, if more of Cu2 plus ions is formed, it means that more zinc solid also will be formed because the reverse reaction is now being favored. More Cu2 plus, more zinc through reduction will also now be formed, moving from zinc 2 plus back into. Now we're going back from here because of Le Chatelier's principle. Now, what will happen? A new equilibrium will be attained so that the rate of the forward and the rate of the reverse becomes equal, and then we have a state of dynamic equilibrium. Once we get to the state of dynamic equilibrium, at this point, the E naught of this cell becomes 0 volt because there is no more potential difference. There is no more potential difference. I'd like to re-explain this again quickly. Remember, we have this reaction taking place. This copper 2 plus is being reduced, as we saw, reduced to copper solid. This creates a stress on its own. So equilibrium will shift to favor the formation of Cu2 plus to minimize the stress. Because once this is minimized, then the equilibrium, we have a new equilibrium, and we say that the rate of the forward and the rate of the reverse becomes equal, and then we have a dynamic equilibrium, which means our E cell is 0. Quickly, what does this mean? If we're taking down notes, what is the meaning of this? Number one, this means that our cell is flat. That's the big implication. But let's explain that. It means that the reaction is no longer converting the chemical potential energy. Chemical potential energy. You can pause if you write this note to electrical. There's no more conversion because the rate is just the same. Electrical potential energy. The rate at which these reactions are taking place are the same. All right? Then we say that the concentration of the reactants and the concentration of the products are now constant because equilibrium has been reached. And number 3, we can say that there is no deficit or excess electrons available for movement. And this explains it all. All right? On the electrodes, there are no deficit electrons. Remember what we said, that the other ones, we have a partially positive and partially negative due to the number of electrons. But now that this is no longer the case. So finally, since there is no deficit, there is no potential difference. Potential difference now becomes what? 0. Zero comma 0 volts, which means there's no current. I also equals to 0. Our cell is flat. This is why you throw your battery away after a while. Remember, the value was 1,1 volt, and as time goes on, the equilibrium is reached. It now gets to 0 volts. All right, this is the end of this session. Please rewind it over and over again. It's quite a long session, it's an hour session. Over and over again. If you understand this, the other sessions just fall in place along this. We might mention a few things, new things here and there, but simply it's just follow through this. I hope this presentation helps you. Again, this is presentation from Krazifizix on galvanic cell. This is our first presentation on galvanic cell. Watch out for the next one. Thank you